Okay, so captured zeros, those are zeros in the middle, in between non-zero digits. So we have 0.0040008. These ones on the right-hand side, or sorry, on the left-hand side. I'm bad with my left and right. If I say left, but it's on the right, then please correct me because I tend to say the wrong one. Like I know which side I'm talking about, but I'll say the wrong one. Those ones are on the left, and those are not significant. So those are our no. Captured zeros, those are the ones in the middle, between non-zero digits, and those are yes. So how many sig figs in this number altogether? There are 1, 2, 3, 4, 5 sig figs. And then finally, our last rule for zeros is what? Yeah? Yeah, our trailing zeros. Are they? Yes.
Them being insignificant or not insignificant depends if there's a decimal or not.
Yeah, it depends if there's a decimal or not. Decimal, decimal. Decimal, yes. Significant, yes. Decimal, no. Hello. What can I do for you? Oh, you got a little thing. Thank you very much. All right, Anna. Hello. We're just reviewing the sig fig rules for zeros. So decimal, no. Significant, no. And the only other weird little bit we have is the overbar. So I'll make this kind of like number 4. The overbar is used only on a 0. And it is only used if you need to show that 0 is your last sig fig. Okay, that it is that 0 is the uncertain digit. So let's just go through a bunch of little examples here, although I think we have some probably in your workbook. So let me just take a look and see if we can use some of the examples that are already there. That would be on page 97, I think. Yes.
For the example of the number 6,000.
Yes, if the number is 6,000.
The overbar of the second to last.
Yeah. So for example, let's say we have this.
Yeah, so that's uncertainty, but the zero afterwards is not uncertainty.
Yeah, this is 3 sig figs. What this number means is that it is 6,000 plus or minus 10. So this would be, it could be up to 6010 or down to 599090. I can do math. Sure, I can. So it could be as big as 6,010. It could be as small as 5,990.
So this only happens if the measuring device doesn't go up to the tens.
It only happens if your measuring device does not measure to the ones.
Or the ones.
Okay. And if we had, like, let's say we had this next one, all right, 6000. Okay. What that means, 6000, that would be plus or minus 100. Okay, so with this could be between the number could be 6,100, it could be 6,000, or it could be 5,900. Okay.
But
and then if we did this, and we had our overbar here, this would be 6,000. That is our uncertain digit right there with the overbar over top of it. And that would be plus or minus 1. So this could be 6,001. It could be 6,000, or it could be 5,999. Yeah? And if you really dislike the overbar, you can always be like, you know what? I'm just going to write this in scientific notation. Okay? So scientific notation, all of these are 6 times 1,000, yes? And that is 6 times 10 times 10 times 10, which means 6 times 10 to the 3. So this would be 6, This one here would be 6. It doesn't want to make a 6, so I'm just going to make a 6. 6.00 times 10 to the 3. At this point, I would not put an overbar over that last 0 because the decimal says it's a sig fig. I don't need to indicate that it's a sig fig. Okay? And I don't have a fourth or a third 0, so I know that I have 3 sig figs. So this here, 3 sig figs. This here, 3 sig figs. Second one would be 6.0 times 10 to the 3. Okay, 2 sig figs. 2 sig figs. And then our last one, this would be, you could write it as 6.000 times 10 to the 3. Or if you wanted to, you could write it as 6000 decimal, which would also indicate that that last 0 is significant. All of these have 4 sig figs. 4 sig figs. 4 sig figs. Okay? And just so you get like a little quick practice today in on that, I would like you to right now just very quickly do page 98. And I will let you know, I've had people already come and ask me for clarification on things during flex, after school. They're the people who are going to, if you got it right away, you know, you've done it in physics, you know it already, that's fine. But if you have any sort of clarification that you need, the only way you're going to get it is to ask. So make sure you ask if there's anything you're unsure about. So give those a try and check with the answer key. Okay, page 98. Do and check with answer key and ask questions.
So the way I did it was I said 6. But the way I did the figure was I said 6,006 times. Yeah. And 1,000 is 10 times the I'm not. I am multiplying 6.000. So it's a 6 times 10 to the 3. Yeah. Yeah, that's what it's like. Yeah. Yeah. 4. Yes. Yes. Yeah. That's correct. Yeah, just one. Yeah.
For this one.
Okay, so like this one. Zeros on the right.
Oh, yeah.
Yes. So is that one 6? Yeah. Okay. Yeah, exactly. Yeah. Okay. Yeah. Is there anyone who would like to sign out one of our extra practice books that have been textbook? You can take it home with you.
Yeah. What I'll do is I'll bring you a book card. You can go grab yourself a copy. And just fill in the book card and sign it out. Because they will have some extra practice. So maybe over the weekend, if you're like, oh, I need to study for that quiz on Tuesday, you're able to have that. Anyone else want to have in?
There you go. Yeah, I'm pretty sure. So, ladies and gentlemen, these books are back here in this corner. So if you have a book card, you can sign one out. So if you would like a copy of this, just ask me for a book card and you can sign one out. You can take it home, just leave it at home. We have lots of copies here, so if you need to use it here, you can use it here. Okay, anyone else want a book card? Maybe later? Okay, good stuff. Yes.
The zero is after this one.
It is significant because any zero on the right-hand side is significant only if there is a decimal. So there is a decimal, so it is.
Even if this one is after the zero.
Doesn't matter. Yeah.
So anywhere the decimal is.
As long as there's a decimal anywhere in the number, those zeros on the right count. Yeah.
So we have this one.
Yes. However, we have five or three ones, but yes. This one is in between ones. So that's like a one in the middle. He's and then you have here, and then you say, here's their why. So that's what is that great.
So bad though, I had him in French too.
So, yeah.
Yeah. Flying. I know. Engineering. Come on, take your time. I don't know.
Yes.
Not the compromise. Like they're.
Oh, no, I can tell.
Actually,
Yeah.
this one's. So yeah, let's start off by
No, it does not, because you're gonna look at me and say, well, yeah, also, you can just look here and say, oh, I need 1.5.
Now, yes, we didn't say. She wasn't pageant. It's just this one. Yeah, and not good. Yeah. But these school ride was.
Yeah. Yeah. And you know what? Perfect. Yes, very nice. Is there anyone who I haven't come around to see and ask how you're doing? Anyone have any questions? No, don't. No, it's all good. That's like, so that's no. No. That zero is how, Hello. Yes. Uh-huh.
But, for K,
Hey,
letter K,
yes,
fourth underline.
yes. It's not zero.
The last two, oh, the last.
K is the uncertain. Yeah. Folks, if you have done the first part of that, I don't know if you've all completed the second part of it. That is 1.5b. Oh no, 1.5a, sorry. Make sure that you go through, and I think, do you guys have this in your book? Yeah, it says, oh, yeah, in any measurement, the last sig fig is the uncertain digit. I'm missing it on my copy here. That's really weird. Yours has it though, yes? Question 4. If you've not done question 4 yet, make sure you go through and do question 4 so you know which digit is uncertain. That will also be on the quiz on Tuesday, okay? So for example, if we did our very first one here, we can circle our uncertain digit or underline it. That would be the 2, okay? So go through and try them and check with your answer key to make sure you are good. If you're bored and you want to work ahead, you can certainly go and read about exact and inexact numbers on page 100, but work on anything you want, really, to be honest. Yeah. What's the significance of this? You know, like what position you're running. So, like, if I said I have this dinosaur that's 5 million years old, like next year it's 5 million years old, right? So, do I actually mean 5 million, or do I mean like somewhere else, some sort of 100,000s, or yeah?
So why would the zero count?
Because your measuring device did not go beyond that. It did not go beyond the tens. The measuring device. Yeah. Yeah, it's a little confusing. Yeah. Yeah. All right.
It's your, you know what? It's your uncertain.
Well, you have 4 signatures for one type of thing, 4, that was last one.
Well, because it was way too easy.
Five.
I wanted to get the like my friend would know. Yeah. I know. With the volume for the grades. Okay. Yeah. We're doing dimensional analysis right now. Dimensional analysis. No. We really keep, obviously. Yeah. Oh, the MS thing. No.
Yeah.
No. So it's meant to be first, okay. And then the same for January.
Put together for me.
The girl being she said you had this.
I just
I know, right? I don't know why he is coming. Yeah. You'd be like racist. It'll be like super funny.
Okay, I've been noticing a lot of people are having the same questions. So I'm gonna go over a few of these together. When it comes to identifying the uncertain digit. Okay? So for this first one, we had one sig fig. And if we only have one sig fig, that's going to be our uncertain digit. That's it. So this one is uncertain. In our next one, we have 2 sig figs. So you say, who are my significant figures? My 2 significant figures are 1, 2. It's the last of those sig figs that is the uncertain digit. So it's going to be this one. Now, people get really excited because we do the next one and we say, oh, there's 3 sig figs here and it's the last one. And then they think, oh, it's always going to be the last one. And in fact, with our next one, there are 1, 2, 3, 4 sig figs.
and it is the 1, 2, 3, 4th digit that is uncertain. But with our next one, we have only one sig fig because there is no decimal in the number. Those zeros are not significant. So this is my one sig fig. So that's my uncertain digit. Okay, and if I had, say, 56,000, no decimal, how many sig figs in that one? 2 sig figs. Who is the uncertain digit? The 6 is the uncertain digit because you go 1, 2, and it's that second one. Okay, so make sure that you have gone through those and that you're getting them correct, because sometimes, a lot of the time, it is the last digit. If there is a decimal in the number, it is always the last digit. Okay, sometimes if I had 4,342, even though there is no decimal, that's my uncertain digit because all of them are significant. But if I had 7,400, I have 1, 2, 3, 4 sig figs, and my uncertain digit is the 4th one. Is that making it make more sense? Yeah? Okay. So make sure you have gone through those. If you didn't finish any of them, that will be for homework. Come in and ask me questions if you don't get it. Right now, what we're going to do is we're going to go back to particles because we've done a lot of mathy stuff. We might as well do some particles. We were around page 46-ish. We just passed page 46. Yeah. I think we're on 47, actually. Yeah, 47. So yeah, when last we left, we were talking about elements and compounds. And we were also talking about molecules. What do you guys remember about molecules? Tell your partner anything you can remember about molecules. All right, lovely class. Please tell me one thing about a molecule. Anything about a molecule. One thing.
They are elements that are bonded together by, or they're non-metals.
Non-metals, yes. Non-metal atoms.
Yeah.
Bonded together. Excellent. So we have one thing about molecules. Anyone know anything else about molecules? What type of bond?
Covalent.
By covalent bonds. Okay, and that's a pretty good definition of a molecule. Okay, molecules. I could say groups of non-metal atoms bonded together by covalent bonds. Yeah, those covalent bonds, those are strong. And the other thing we need to add is that molecules are also neutral. What do I mean by neutral? They are not positive, they are not negative. They have a 0 overall charge. I'm actually going to get rid of that. I'm going to put that there. Groups of nonmetal atoms. They are not positive or negative. Yeah. Okay.
They're stable.
They're stable. And in fact, the atoms in the molecules aren't positive or negative either.
Oh, really?
The atoms in the molecules are also neutral. So we could put that in there.
I thought all atoms do.
They all contain charges, but the atoms themselves are neutral because they have the same number of protons and electrons. Yep. And I am going to show you my abbreviation for molecule. MC, capital M, capital C. We write the word molecule a lot. So it's nice to have a nice little abbreviation for it. Okay? So the atoms in the MC in the molecule are also neutral. Those covalent bonds are strong. Does anyone know anything else about covalent bonds? You can chat with your neighbor about that if you like to. Anything else about covalent bonds that you know? Yeah? Yeah, they're sharing their electrons with the other atom, okay? Covalent bonds is sharing of electrons. Okay, so we've got a very sort of robust, thorough discussion of what a molecule is. All right? And we can see where we got to last day with that. We had our little hydrogen molecule, and each hydrogen had a single electron. Is that a stable state or an unstable state? Stable means happy. Unstable means unhappy. It is an unstable state. They would rather have their outer shell be full. And how many electrons fills shell number 1? 2 electrons. So hydrogen is good at this point. So now the formula for a hydrogen molecule is H2. The reason I'm drawing your attention to the word formula is that very often, because in math, formula and equation are often used interchangeably. Yeah, in math, you've got a formula, you've got an equation. In chemistry, the formula is like, how do I represent this chemical, this one chemical? Yeah? An equation is when you have a reaction, this plus this, arrow that. Okay, so right now we're just dealing with formulas. And the formulas are the symbols for a chemical. Hydrogen is made of 2 atoms. Therefore, it is called a what kind of molecule? A diatomic. And that's because di means 2. So we have hydrogen, nitrogen, oxygen, and chlorine also exist as diatomic molecules which contain 2 atoms. Could you please write the formulas for nitrogen, oxygen, and chlorine? So are they correct as they are, or do we need to add something else? We need to add a 2 to all of them. Do we put the 2 up here?
No.
No. Where do we put the 2? At the bottom. Subscript. Okay, N2O2, Cl2. And these molecules are bonded together covalently. They're sharing their electrons. These are molecular elements. They're not compounds. Okay? not compounds. But now we're going to look at compounds. So you can have molecules that are elements. You can have molecules that are compounds. So if I were to ask you, are all molecules compounds? Are all molecules compounds? The answer is no. Why? Tell your neighbor. Why? The answer is no, because some molecules are not compounds, but elements. For example, H2. Why did I put a star beside that? Because I love to ask this question on tests. Love it. Love it. One of my favorite questions. The other one is, are all compounds molecules? That's my other favorite question. We'll get to that one soon. Okay. So just backing up for a moment here, we have when two or more different elements react in a chemical reaction, the atoms do not just mix together. If we have a reaction, they become joined. What's the word we use for joined in chemistry?
Bonded.
Bonded. And they become bonded with one another to make a compound. So over here we have hydrogen, which is an element, because all the atoms are the same. Okay? In an element, all atoms are the same. We have oxygen. Which is a different element. Oh, now I've made it look black. That doesn't make me happy. Maybe I'll just circle it in blue. Okay. All the atoms are the same. But when we have water, water is a what? Compound. Because the particles contain different atoms. The molecules, the MCs, contain different atoms. So that's the difference between an element and a compound. All right. Yes.
Is there like a certain formula? I want to say formula not the right word. Is there like a certain way to determine what atoms might have stronger bonds compared to what atoms bonds?
Like with each other?
Each other, yeah.
To a certain extent, yes. If you have atoms that are smaller, they will be more attracted to each other, because what's actually happening, do you remember our little drama that we did last day where we all got up and we held a pencil and we held a pencil and we pulled on them, okay? The strength of that pull depends on how far the positive and negative are away. So if I was the nucleus and I was positive and those electrons that we were holding were negative, I am pulling on that negative charge. If I am a smaller atom and my electrons are closer to my nucleus, I'm pulling harder.
Oh.
So like if I have a magnet, where's my magnet? Where did it go? Okay, I don't have a good magnet for this. This makes me very sad. That's okay. Oh, here it is. Okay. Even at that, it's really hard to show this because I don't really want to drop the magnet because that tends to demagnetize it. But if I were to hold my magnet here and I let it go, it does not, it's not strongly enough attracted to the board that it, but if I hold it about a centimeter away and I let go, right, it is attracted enough that it will hit the board before falling. So the closer the electrons are to the nucleus, so if you have a smaller atom, so things like hydrogen, fluorine is in period 1, it's only got 2 shells. So things at the top of the periodic table tend to have stronger bonds than things near the bottom of the periodic table where they have more electrons and more shells.
Right.
Those will have weaker bonds.
Right.
Because their electrons are way out here. You can imagine if I was like holding on to them out here, I'd be like,
Yeah.
you don't have as much pull.
Yeah.
Yeah. Okay. There's also tables where you can look these things up.
Yeah, sure.
Yeah. Yeah. Okay, so here we have some molecules of compounds. And we know that the formula of water is H2O. Would I ever write a 1 here? No, that would be, it looks ridiculous, right? Because you've been doing chemical formulas for years now, yes? More or less, a couple of years, grade 9, grade 10. Plus water is so familiar, no one would ever say H2O1. What is the formula for carbon dioxide? CO2, because we have 1 carbon and 2 oxygens. So what do those subscripts tell you? They tell you they tell you how many atoms of that type. Nope. That's okay, we'll come to that later. It's okay, we'll come to that later. Just all in good time, okay? And if there is no subscript, that means there's just 1. Now, the reason it doesn't tell you the charge is because it just doesn't tell you the charge. Do you remember what we said about molecules? Do the atoms in the molecules have a charge?
No.
No. Everything's neutral. The atoms are neutral. The molecule is neutral. Okay? Everyone has a balanced number of protons and electrons. So everyone has a net charge of 0. Okay, now we are coming to a different type of compound. Here we have, has anyone heard the term crystal lattice? Bam, my student in grade 9. Okay, because I get a little wacky in grade 9 and I go all to town on it, but that's okay. You don't need to have heard it. Have you ever seen salt crystals? Yes, okay, on your dinner table, perhaps, if you spill some and got some on your plate there. Salt forms crystals, and we call it a crystal lattice, okay? And what it is it is 3-dimensional, and it consists of alternating positive, negative, positive, negative, positive, negative, positive, negative. And it doesn't just do it positive, negative, positive, negative, positive, negative in one direction. It also does positive, negative, forward and backward, and it does positive, negative, up and down. Yeah? Sideways? back and forth, up and down. So you can see here is our actual three-dimensional model here, where we have the positive ion alternating with the negative ion, and you can see it in this picture here, where we have our positive ion alternating with our negative ion. Why do the positives always find themselves in between the negatives? Why don't I have a negative and a negative? Have a chat with your neighbor about that. Why does it always go plus, minus, plus, minus? Why not plus, plus, minus, minus?
Cancel out. That's right. We chart.
Yeah, it doesn't look right, but what's wrong with it?
There was like certain well, you have to like first look at like how the curve.
I'm loving seeing people's fists do this,
Yeah,
because that's exactly
yeah.
what's going on. Okay, if I put a positive and a positive side by side, what do? They repel. Okay, so this is unstable. Unstable means if you put it there, it will try to not be in that arrangement.
Yeah.
Okay? This arrangement, on the other hand, is stable because positive attracts negative, whereas positive would repel positive and negative would repel negative. Okay? Now, I'm not expecting you guys to be able to draw a 3D crystal lattice. That looks very complicated. I certainly couldn't do it. I am not an artist at all. But you should be able to draw a two-dimensional slice. Yeah? So if you just took one face of this, positive alternating with negative. Any questions? Okay. So this 3D crystal is called a what? A crystal lattice, not lettuce, but lattice. When we write the formula for these, now what types of compounds are these? Are these covalent compounds? No, what kind of compounds are these? They are made of ions. They are ionic compounds. When we write the formula for these ionic compounds, we use the smallest whole number ratio.
Oh, yeah.
Okay? Because you might have a slice of a crystal that looks like this. And in this case, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 sodium for 8 chlorides. But we don't write Na8Cl8. Okay? We don't do that. We just say it's 1-to-1. Because you might have a different sized crystal. Let's say over here. And this one has 1, 2, 3, 1, 2, 3, 1, 2, 3. So it's 3 by 3 by 3 sodiums.
3 by 3 by 3 is what, 27?
Yeah.
Okay, so this would be, did I do that right? 3 by 3 by 3. The answer is 9 times 3 is 27. Okay, so there would be 27 sodiums for every, that doesn't sound like enough. 1, 2, 3, 4. No, anyway, let's just pretend there's 27. I'm obviously not doing my math correctly. Someone can correct me along the way. I know one of you out there is probably brilliant enough to go, no, there should be this many. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Why are there 18? Oh, I see. Yeah. Okay. So there's 18 in each slice.
Yeah.
Okay, and we have 1, 2, 3, 4, 5, 6 slices. We have 6 slices. So 6 times 18 is 108. Look at you do that in your head like a genius. Wow. Okay, so we have 108 sodiums and 108 chlorides. Would it make sense for me to write the formula as Na 108 Cl 108? No, that is ridiculous because the next day I might come across a sodium crystal that has that many sodiums and that many chlorides. I can't be changing the subscripts every time I get a different size crystal. That's ridiculous. So when we have an ionic compound, we use the simplest ratio, which is always for sodium chloride 1 to 1. Okay? So we use the smallest whole number ratio between the ions. In sodium, there is 1 sodium for every 1 chloride, so the formula is NaCl. Notice there's no subscript, so that means 1 each. That's different from H2O. Can you ever have a different number of hydrogens in water? No, it's always H2. It's not going to be like H4O2. It just isn't. Water is always a little Mickey Mouse, right? It's never like double Mickey Mouse. Okay? We're going to take a look at mixtures versus compounds. Which one of these is a mixture and which is a compound? The one on the left is a mixture because the oxygen is separate from the hydrogen. You can see that they are not bonded. O and H are separate. They're mixed, but they're separate. But over in water, is that a mixture? Yes?
You say it's kind of like with oil, and when oil is placed in water and it flows to the top.
That's a mixture. It's a heterogeneous mixture.
Because it's not.
Yeah.
It's not soluble in water.
Yeah. Okay, if you look at all the particles here, every single particle looks like Mickey Mouse. I got a Mickey Mouse here. I got a Mickey Mouse here. I got a Mickey Mouse here. And I got a Mickey Mouse here. All the molecules are the same. So all the MCs are the same. So is this a pure substance or is this a mixture?
This is a pure substance. And it is no longer an element, it is a compound.
3 dots.
Oh, the 3 dots mean therefore.
Oh, 4.
Sorry, I thought I had taught you guys that. It must have been my other block. Okay. And let's see where we're at. On page, what page is that on? That is on page 48. Okay, so why is it safe to put sodium chloride on your fish and chips, but it is not safe to use sodium and chlorine? You're gonna die. We'll actually see later when we get to the element, the atoms in the periodic table unit, we will put some sodium metal in water, and it is the one that goes bang. Okay, you would not want it hitting the saliva in your mouth and going bang in your mouth. Like it literally catches on fire and then explodes. So the properties of a compound are very different than the properties of each individual element. Sodium chloride, the compound, is safe to eat. Sodium and chlorine, the elements, if you breathe chlorine gas, you will die. If you eat sodium, you will die. If you have too much sodium chloride, you might get high blood pressure and eventually die, but for most people, a little bit of salt is fine. Yes?
Oh my god. Basically, I don't remember a lot of science and we did this, and it was last.
Yeah.
Like me, a year and a half. But there's also like the neutralization effects too that's brought into like salt like that, right?
Yeah.
And bases.
Yeah.
So depending on what's being bonded together, they can be neutralized or separate. They can be really big just for you, like sodium and chlorine.
Yeah. And part of the reason is, do you remember the atoms like to have their shells full? Well, sodium does not have a full shell. Chlorine does not have a full shell. Those are unstable. When the electron transfers from sodium to chloride, it leaves sodium with a full shell and it leaves chlorine with a full shell, and everybody's happy and stable, and so there's a release of energy. So the properties of a compound are different from its elements by themselves. Okay, and I'm going to give you for homework pages 50, 51 to 50, 50 to 52, 50 to 52, and study for your accuracy and precision quiz.
So we're going to do data sets and we're going to do a definition records and
Yep. So if you have not yet checked out on Teams the upcoming quizzes and tests, there's a little bit of detail in there on what's on the quiz. How many of you have checked out Teams for the quiz? How many have not checked out Teams for the quiz? If you've raised your hand for I've not done it yet, please do so because it does give you a little bit more detail. I'll just show you that really quickly right now. Upcoming quizzes and tests. Like it literally says there will be a question with targets. There will be a data set where you need to take the average to determine the accuracy. There will be some definition related questions. Extra practice is on page 40. There is only one retake for this quiz. So you can often find like a little bit of extra detail in the upcoming quizzes and tests section. Okay? Quiz on units on Monday. Quiz on counting sig figs on Tuesday.
I thought it was on Monday.
Units on Monday.
Oh,
Counting sig figs Tuesday.
unit, what?
Meters,
Oh,
meters,
no.
moles, and Kelvin, kilograms, and seconds.
Oh, maybe tomorrow. Yeah, so we don't forget.
How to memorize the value for moles? Or
Eventually, but not right now. Yeah.
and can I get the I think I'm
Oh, yeah, for sure. Here, let me just, there we go. So all the molecules are the same. Yeah.
What's the with units on Monday?
Oh, liters, meters, moles, and Kelvin, kilograms, and seconds.
Oh, it's just about the units.
It's just the units. It's literally, you know, that little table
Well, I
that we
thought
did?
like about the measurement unit.
No, it's just like which unit goes with which quantity.
Thanks.
Yeah, easy. Thank you. If you signed out a book, please make sure I get the book card. Okay?
No, I did finish.